Acho que é.
Pois é, última aula.
Sim, última aula. Outra coisa, professora, ficou decidido sobre o retorno, a data?
Então, me responderam várias pessoas, só que eu realmente não tive tempo de fazer o check-in. Quem respondeu, não respondeu, quem pode responder. Ou seja, eu vou confirmar com vocês até o final da semana, pode ser?
Sim, claro.
Sim, tranquilo.
Show de bola. So let's speak English now. Natalia asked me to show some batteries, compare some batteries, and I thought that it's better to compare batteries that have the same purpose. So I was looking for batteries for home storage, so electricity storage in a home or business. And well, we can compare these batteries. Most of them, well, all of them are lithium-ion batteries. Some are lithium, nickel, manganese, cobalt batteries. Others are lithium, iron, phosphate batteries. They are not lithium cobalt, so cars usually use lithium cobalt because of the energy density is higher. In here we can see that, for example, the warranties are increasing. Overall, you have 10-year warranty. If the battery lowers the capacity, the potential of storage lower than 60, EOL is end of life. So, for example, if the capacity lowers to 50% before 10 years, you can probably charge them and ask them a new battery or something like this. So other batteries are only 5 years warranties. So
Professor, are you presenting?
No. Thanks for my screen so much.
Yeah, thank you.
Right. Thanks so much. So 10 years, EOL is here is end of life, 60%. So if it goes lower than 60%, you can use a warranty to get some money back. Most of them lithium, nickel, manganese, cobalt. You have some lithium, iron, phosphate, and that's it. Only these two. They are cheaper, they have higher energy densities, but they are good enough for battery home storage. There's also battery home storage. You don't want huge battery. You need to be small also in order to fit in a house, in an apartment, for example. But the costs vary significantly. You have, for example, the cheapest one is SunGrow, and this is much more expensive than the one that I showed you, which is $200, the container. And I was looking at the average costs per year that I estimated, and I found it to be too high, the ones that I calculated, because the cost is only 200 and here is much higher. So then, yeah, so I made a mistake, right? I made a mistake, and I want to tell you guys that I made a mistake, and I want to correct myself. So, but these are kind of like an overview. I'm going to send you the PDF. There's, you can have a look at different different batteries, different companies. But one thing that's helped me a lot is this graph is that, yes, I made a mistake on the way I was calculating the costs. It was a very bad mistake, so I'm very sorry for that. Of course, every time I find something a mistake that I make, I'll let you know. But it's good to find out these mistakes because in the future you don't make more mistakes. So please let me know if I say something that doesn't sound right, and that'll be great. The thing is, so to calculate the cost with this discount factor, the idea is that you want to bring all the costs to today's costs. Given that a battery is like a boiler, you add to a system. You don't need anyone to operate the battery, operate by itself. So the capital cost is the main cost. And then you bring all the costs for this year costs, and then you have to look at how much energy you generate from the storage, how much of the energy of the storage you actually use in order to be able to calculate what's the cost for storage, the levelized cost for storage. And in the calculation, yes, I have the discount factor, but I was dividing by the days, the amount of days in the year. But really what we want is the amount of hours, because we're assuming here that we have 1 kilowatt hour battery potential that we can use. And this kilowatt hour, here is megawatt hour, but this kilowatt hour is how many kilowatt hours I can generate with 1 kilowatt battery. Is the amount of hours in the year times the capacity factor, how much of this capacity is actually being used. The capacity factor is never bigger than 50% because it's going to use the 50% of the other time. So usually batteries have 10 to 20% capacity factors. Very small capacity factors. Pump storage plants, seasonal pump storage plants have maybe 30, 40% capacity factors. Batteries vary from 20 to 5%. So this is the maximum amount of kilowatts you could generate with this battery. Of course, you have to charge in order to release the energy. So this is just a number. And then the capacity factor, which is the important bit that you multiply by the number of years that you have, right? Number of hours that you have in the year. And then if you make this calculation, you have that the cost is $24.8 per megawatt hour, which is relatively equivalent to these costs. If you compare this cost to the investment cost with the levelized cost. And if you multiply by 4.5, you have 133 reals per megawatt hour. This is a little bit cheaper than, for example, wind power. So today, if you look at the auctions for wind generation in Brazil, the cost is between 180, 150 reals per megawatt hour. So it's comparable with the price of wind power, but we're talking about something that stores energy. So it's much better for you to invest in wind power and generate electricity than investing in batteries to store electricity. But if you have a lot of wind power, if you have a lot of solar power and you need storage, of course, it will make sense to invest in a battery. And for example, Brazil, we will change from seasonal weekly PLD, is preço líquido de diferença, and it's going to vary hourly in next month. So for example, if you have a battery that the cost of the battery this for storage is 136 reals per megawatt hour, and you have in the whole year that you have these fluctuations. Imagine you don't have these scenarios where the electricity is low and the variations are low. You have variations of around 100 reals per megawatt hour, which doesn't pay for the battery. Even if you have next year a scenario where you have these prices variation, the battery is not going to be you won't be able to pay your battery. But of course, if you have a lot of scenarios like these where the cost jumps from 200 700, this is not the PLD, sorry, this is the CMER, because the PLD stops at 500. So if you have the costs varying from 200 to 500, you have 300 reals per megawatt hour prices differences. So then if you have this battery with these characteristics, it will make sense to invest in a battery, lithium-ion battery. Looking at this variation in costs, I would say that it is still not a viable solution to invest in battery. Maybe if you have a business and you buy electricity from the Mercado Livre, because this is the cost for electricity for who is generating electricity receives money. This is the amount of money they receive for generating electricity. The person that is buying the electricity also has to pay this amount of money according to the PLD horário. And if they have a business and they put a battery in their close to the demand, they can make contracts with the distribution system.
Flavio is trying to join the class.
Thank you. So sorry for this confusion. It's megawatt hours, not megawatts day. I made that mistake. So the cost is much more competitive than we were talking about, but it's still not a viable alternative for storing electricity with the PLD. Let's go back. The PLD. But maybe in 5 years' time, the cost will, instead of be 130 reals per megawatt, will be 50, and there will be a lot of people investing on batteries, particularly for energy storage in hospitals, shopping centers, and all these other demands. So now we're going to start talking about the lecture 8. Lecture 8 is about thermal energy storage. We're going to go through the theory behind thermal energy storage. We're going to talk about the combined heat and power with thermal energy storage, electricity generation with thermal energy storage, electricity storage with thermal energy storage, heat thermal energy storage, cooling thermal energy storage, low temperature phase change materials for energy storage, and about seawater air conditioning. So regarding the theory for the thermal energy storage, you have thermal, which can be sensitive heating, liquid, solids, or gases. You have latent heat, which is the phase change of between solid and liquid, liquid and gas, solids and solid. Solid and liquid, liquid to gas. Yeah, there are only these two, solid to solid. I have no idea what should have looked into this. So the other one is chemical energy storage. If you change the the composition. For example, heat pump, you have a refrigerator, different type of heat pumps with chemical energy storage. The idea is that you change the composition of the components and then you lose heat or you gain heat. So for this phase change and sensible heat, the latent heat storage, you have heat is equal to the mass of the material that you will pass through phase change, and then you have L, which is the latent heat. Usually latent heat is interesting because it maintains the temperature the same throughout the whole process. Sometimes if you have a mixture of components, you have a little bit of increase in change of temperature while the components change phases. If you have a mixture of components, and this brings advantages because with a designed temperature for you to store heat, then release heat, this is convenient to improve the efficiency of heat exchangers. But latent heat has a disadvantage because when you change phases, the thermal conductivity of the material changes substantially, particularly when it solidifies the heat conductivity for you to be able to extract heat or remove heat or add heat to a system reduces substantially. So in these cases where you have this problem, you can use sensible heat, which can be in liquid form, gas form, or solid form. If, for example, the solid has a very good thermal heat conductivity, then the thermal heat conductivity doesn't change and you still can use it. And so these are the main ones, latent heat and specific heat, but then you have another one which is literally mass balance. If you have an energy storage tank and then you fill up with hot water, of course the hot water is not going to change temperature, it's not going to change phase, you just fill it up and then you release it. You have advantages because you can store much more energy per volume if you do it like this. You don't have to change the phase or change the temperature. However, the disadvantage that you have to find the energy carrier in order to replenish the water. So you have to have a source of water, or you have to recycle the water that you use in the storage tank. So this is another approach for storing energy. It's literally just filling up a tank, or you can. Another alternative is to use a steam storage vessel. So, but steam, you have to increase the pressure, right? So steam to a pressure vessel, but you have to put pressure, put energy in order to increase the pressure. But it's also a possibility. Regarding the technologies, this is a graph that shows the different energy storage technologies. We have thermochemical, which is still under development, molten salt, ice storage, residential hot water heaters, cold water storage, underground thermal energy storage, peat storage. We're going to go through most of these in the next slides. And I wanted to start with one alternative, which not many people talk about, but has a lot of potential and is very much used in the industry, and people don't talk about it, but it's a very good thermal energy storage solution, which is combined heat and power thermal energy storage. So for example, if you have a combined heat and power solution, what happens is that if you want to use the heat the waste heat at low temperature in order to improve the energy efficiency of the system, and you have heat demand. So for example, you want to burn coal, and you want to produce electricity and heat. You can produce electricity and heat with much less coal than if you generate only electricity with the coal, and then you burn more coal to provide the heat. So this is the combined heat and power. I'm sure you guys heard about this in the past. But the thing is that with this solution, the efficiency for electricity generation is around 35%. You lose a little bit of efficiency in order to, because the low graded heat is turned into, is used for heat demand. But on the other hand, for example, if you don't want, if your heat demand varies, or for example, the electricity prices increases substantially, which it makes more sense for you to generate more electricity than actually using the waste heat to supply your heat demand, you can just increase the efficiency. So use this low graded heat to produce more electricity and stop supplying the demand. Or another alternative is that you have a thermal energy storage tank where while supplying the electricity heat demand with the waste heat and supplying the demand, but then you need to increase the efficiency of your electricity generation. So you stop producing waste heat. You stop supplying the waste heat with your solution. So it goes still a loss to waste, but then you can take the energy that you stored. So you store the energy while you're operating your system, and then this energy stored with thermal energy storage solutions, several solutions that we'll talk about, and this can supply the heat demand. So combined heat and power solutions, there are several uses, several reasons why you would want to use this, but the main gargalo is the heat demand. Sometimes you don't have heat demand in a location. Sometimes you have only a little bit of heat demand in a location. So for example, if you have only a little bit of heat demand, you can use storage, add a thermal energy storage solution, and perform the system this way. So you can be more flexible in how much electricity you can take out from your thermal electricity solution. Has anyone ever seen this solution before, by the way? Has everyone heard about this?
No, not really. Should I have one question? I didn't understand why we have 40 and 65.
Oh, thanks. Yeah, so 40 and 60. So I did the slide.
It's okay, I was just a little confused. Thank you.
That's a great point. Thanks a lot for correcting me with this. Yeah, so if you have, for example, a heat demand, you can store the excess heat that you produce, and then you can supply with your storage and increase the flexibility of your electricity supply. So this is both for thermal energy storage and also electricity storage, because you increase the amount of electricity that you come out from the system. So this is one arrangement that you can have that gives you more flexibility and is a storage solution working with combined heat and power. As I mentioned in the previous lecture, so this solid oxide fuel cell, which also is very good for combined heat and power, can also be used with, can also be implemented with thermal energy storage. For example, if the electricity is cheap and there is not so much need for electricity, so it's similar to the other one, to the other case, but given that the heat is a little bit small, given that the solid oxide fuel cell is so much more efficient, the waste heat is much smaller, and then the demand and the heat that you have to store is smaller, and then the gains that you have for your efficiency is smaller. So this is just an example for the solid oxide fuel cell. But the solid oxide fuel cell is already being implemented in homes throughout Europe, mainly in northern countries, in order to provide heating supply. So this combined heat and power storage can be supplied with for small scale in home appliances. Instead of buying electricity and having a boiler, you can supply your needs with a combined heat solution with natural gas or hydrogen in the future with a solid oxide fuel cell, as we talked on hydrogen lecture. In this case, for example, if you have a solid oxide fuel cell boiler in your house, you can use it for producing electricity for you with hydrogen or natural gas. And then you store this electricity, this excess heat, this waste heat, in your thermal energy storage solution. For example, when you want to have a shower or when you need more heat demand during the day, you can stop supplying the storage and then you can supply the heat demand and the storage, thermal energy storage that you stored with the thermal energy storage solution, then you supply also the heat demands. So there's a lot of possibilities that you can work with combined heat and storage with thermal energy storage and improving the system. Of course, that depends on how much. Also, another thing is that, for example, you have a lot of thermal power. So you have electricity, you need to generate electricity, but then you don't need to generate electricity at the same time as your heat demand happens. For example, not looking into a house, but looking into a factory, looking into a business. So then what happens that when you generate electricity, you store the energy, and the energy stored, it can provide you with your heat demands. For combined heat and power solutions in Brazil, you have the potential mainly the amount of heat that you have, so the demand for heat is mainly supplied with biomass, bagaço, cana, coal, gas, and other fuels. So there is a lot of demand for industry, for example, that can be supplied with combined heat and power solutions. Looking into this, having, for example, a solid oxide fuel cell, which operates with natural gas, and then in order to supply all, so this is the electricity demand for industry. Here's the heat demand. What you can do, you can provide all the electricity demand and the heat with a combined heat and power solution. And in order to make it flexible, you add thermal energy storage, which substantially improves the system. So a huge potential for this. For example, the industry is looking for solar heaters, parabolic solar heaters, different type of solutions for heating, but also they should consider this combined heat and power with thermal energy storage. So any questions about combined heat and power and combined heat and power with energy storage? I showed you 3 or 4 different arrangements that you can make in order to increase the viability and make it more flexible for different energy needs. Okay, so
No questions, yeah.
questions? Yeah. No questions. Electricity generation with thermal energy storage. So when you want to generate electricity, you can also use thermal energy storage. And the most important example, the main example, is the concentrated solar power, which is a different alternative for photovoltaic. So solar photovoltaic, this concentrated solar panels, you have several mirrors which focus the solar irradiation to one point. So this is a tower, concentrated solar power plant. There are parabolic, several other different solutions. And given that the sun is not shining throughout the whole day, it's in order to increase the viability of this plant, because it's very expensive to build a steam turbine, a steam cycle, very expensive steam cycles for coal, for any type of solution. If they only relied on solar generation, they would operate with 15% of total capacity, so installed capacity. And if you have a steam turbine that operates at 50% installed capacity, not viable, not an alternative. But if you add thermal energy storage to the system, you can increase the capacity factor of this plant to maybe 60, 70%, 50%, depending on the needs, depending on the quality of the solar irradiation throughout the whole year. Yeah, so in this case, so this solution, this thermal energy solution, is using molten salt, and particularly molten salt which is sensible heat molten salt. And I'm going to go through the advantages, but the main advantage is because the molten salt can flow through. You don't need to have another, for example, steam or another intermediate cool heating carrier in order to melt or freeze this this material. So for concentrated solar power plants, this sensitive heating is the solution that's mostly being used. So there are sensible heat solutions for thermal energy storage. There are latent heat, there are thermochemical, and so sensible heat is the one most used. It's usually a mixture of different salts in order for the thermal capacity to change at different temperatures. They have a mixture of different salts and latent heat, thermal energy storage also. And as I mentioned, the main advantage of sensible heat is that it has a large environmental and commercial feedback. Now, it's easy implemented. The main advantage of sensible heat is the fact that the same material is used within the whole system. You don't need to have another system or extracting the heat from the thermal energy storage tanks. You use the same heat that you store. So the same material that you store in the system is used in order to transfer the heat from the tower to the steam turbine and for the storage. So that's the main benefit. I'm sorry, this paper is not a very good paper. I should have chosen another paper. Disadvantage, low thermal conductivity. So as I mentioned, latent heat, the main advantage is low thermal conductivity, mainly when you solidify the material. When it's solid, for example, salts, they have very low thermal conductivity. So when you melt, you just melt this small part, and then the heat doesn't melt the whole tank. And when you want to freeze, what happens is that when you want to, well, not freeze, but fuse the salts, what happens that you will have the solid around the heat exchanger, and then you won't have exchange heat between the hot fluids inside and your storage tank, which is the main issue with latent heat thermal energy storage. Chemical solutions, there are several chemical solutions. They are also used in different alternatives. The idea is that when you put heat into the system, there is chemical reactions that change the composition of the materials, and this changing composition needs electricity to be put into the system. And then when you want to release energy from the system, you cool down the tank with this chemical energy storage. What happens is that when it reaches a certain temperature, the reversible reaction happens, which also releases heat. So I'm not going to go through all the details of these different solutions, because I'm talking about thermal heat energy solutions, and there are a lot of different alternatives and solutions which I want to go through. I'm not going into details. If anyone wants me to go into details in one of these, for example, please let me know, and I'll do in the next lecture. So this is thermal. So this is sensible heat storage materials. This is latent heat storage materials. This thermochemical storage materials. These are the chemical reactions that happen at different temperatures. Sorry, I was in the wrong slide. Another possibility is to have several stages with different components in order to improve the system, to increase because when you're talking about steam turbine, it's convenient to have temperatures at different temperatures, and in order to better control the temperature that goes into the steam turbine, it's good to make sure that you have the best solution to control the temperature at different levels of the turbine, the steam turbine. So also interesting to have different materials at different latent heat, latent at different temperatures, different fuse temperatures. Also for thermochemical storage solutions, also there are solutions which is a mixture of different components. There's a lot of research going on at the moment, and eventually they'll find the best solution for different locations, for different type of concentrated solar power. So, for example, if you want one plant that generates more electricity during peak hours, so can store electricity for, let's say, 1 day, you can store electricity for 1 week. It's base load solution, or you store electricity and you want to generate very quickly in maybe 3 or 4 hours for peak generation, which is going to be very important in the future. You will need different materials, so different molten salt, different thermochemical components in your solution. As we are all engineers here, that's what engineers do. We have to have the best design, the best components, the best mixture in order to give you the results, the services that you need. The main objective, as I mentioned, is to store concentrated solar during the day. The sun only happens during the day, and then you store this excess electricity that you don't need, and then you shift this electricity to the night or to the early mornings, And another benefit is also that you increase the capacity factor of the system, because, as I mentioned, steam turbines are very expensive. Other alternative is to have a furnace. For example, if you have a day which is windy, it's cloudy, you don't have as much solar radiation that you expected, but at the same time you have a large demand for electricity that you need. The price of electricity is high because other PV solar panels are not generating so much electricity. What you can do, you can combine this system with another thermal electricity system. For example, a furnace burning biomass, burning methane, burning any other fuel. It can be a hydrogen solid oxide fuel cell, combined heat and power, which generates electricity and heat in order to increase electricity from here. And this combined heat and power also can have its own thermal energy solution, as I mentioned in the beginning. So both of them with their own solutions, but they can help each other increase their own efficiency by just operating in synchrony. So I put biomass and hydrogen because we're talking about sustainability in the future, blah, blah, but it can be any fuel combined with this type of systems to increase the reliability of these systems. So this was the main solution for electricity generation with thermal energy storage that exists, this solar thermal energy storage. And now we're going to talk about electricity storage solutions that use thermal energy storage. So for electricity storage solutions that use thermal energy storage, we have this alternative, which is liquid air storage, which is very funny. It's a very innovative, new approach for energy storage. England is developing this. So there's a company in English, is Hydroview, I think. This is now the website Hydroview. So this solution for any electricity storage takes air from the atmosphere. So basically, it doesn't. It only stores cold air, but air at ambient temperature, it just releases hot air after it generates electricity. But in order to store air, it has to liquefy the air surrounding the plant. And the theory behind this technology, the idea behind, is because the Carnot cycle efficiency says that if you have a very cold, so this is the main equation for the Carnot cycle efficiency. So the theoretical efficiency that you can have with thermal energies, thermal solutions. We wouldn't really talk so much about hot, so heating solutions. So with this type of with electricity storage thermal energy solution, we only talk about cold thermal energy solution, because when you're talking about electricity, this one, electricity generation with thermal energy solution, is because when you have a lot of hot, for example, solar power, you have solar collectors generating a lot of heat, you generate electricity, you don't store electricity. You can store electricity in order to improve the efficiency of the system, to improve the viability of the system, but no one's going to just heat up something just for the storage sake of it. They will generate electricity with thermal energy and store some of the thermal energy that they have in order to improve the system. But in this case, no one is going to cool down. There is no option. There are no viable option for you to use a cold source in order to generate electricity. So in this case, liquid air energy storage is only used for electricity storage. It just doesn't generate electricity. And given that the cold source is so cold, very, very cold, this temperature, the cold source temperature divided by the hot temperature source is very small, which results in very high efficiency. So the thermal efficiency of this system is around 75%. So there is this company which has a very nice video, and it will be interesting for you to listen to. They can explain much better how the system works. They can show the graphics of the system, which is much more user-friendly for you to understand with graphics. So I would suggest you guys to put this link, which I'm going to share with you. And then we can watch together.
HiView's liquid air energy storage system consists of three main components. A charging device, which uses off-peak or excess electricity to power an industrial liquefier which produces liquid air. An energy store where the liquid air is held in an insulated tank at low pressure, and a power recovery unit where regasified liquid air is used to drive a turbine and generate electricity. Operating efficiency is enhanced by adding a thermal store and our proprietary cold store. These capture and store waste cold and heat from the process. Here's how it works. Air is first cleaned and dried, and then refrigerated through a series of compression and expansion stages until the air liquefies. This process is based on the Claude cycle, which is over 100 years old. The liquefied air is then stored in insulated tanks at low pressure. These tanks are readily available from the industrial gases industry, or at very large scale, the LNG sector. When power is required, liquid air is drawn from the tanks, pumped to high pressure, reheated and expanded. The resulting high-pressure gas is then used to drive expansion turbine generators. No fuel is burnt in the process, resulting in the exhaust producing clean, dry air. Waste cold from this stage is captured by the cold store. This is later recycled to enhance liquefaction efficiency. And in a similar way, heat generated from compression during recharge is captured by the thermal store. Some of the key benefits of HiView's LAES system are no geographical constraints, unlike pumped hydro or compressed air energy storage, for example. Low capital and operating costs using long-established global equipment suppliers and installers. Long lifetime of over 30 years, with components available off the shelf with thousands of hours of proven operation in many applications. A small footprint and high energy density compared with other energy storage solutions, and no harmful emissions. The system is completely modular and scalable from around 5 megawatts to hundreds of megawatts in power and up to 12 or more hours in duration. It can be built either as a standalone system or co-located near other processes to maximize performance. Large-scale storage offers the opportunity to bank energy and time shift it to periods of peak demand or hold it in reserve. This is critical for intermittent renewable power such as wind or solar, or to move excess off-peak energy to times of peak demand. The HiView LAES configuration is uniquely customizable. For example, the technology can integrate industrial waste heat from peaker plants, or waste heat from industrial plants such as steel mills, or utilize waste coal from LNG terminals, all resulting in improved operating efficiency. And the future? Design work has already begun on HiView's new gigaplant, capable of producing an output of 200 megawatts with a capacity of 1.2 gigawatt hours. HiView, delivering tomorrow's storage with today's technology.
For me, this is one of the best solutions. Transform air into liquids is amazing. You are mute, Julian. Julian, you can hear you.
Thanks so much, Natalia. I'm sorry about this. I'll have to remember. Yes, this is a very, very nice presentation, very nice video of the technology. They have advantages and they have disadvantages, and let's just go through them. So one of the nice advantages is that these towers, in order to store energy, electricity into energy, they are cheap. So cheap to build and to consume energy in order to produce air. So for example, if you have a energy matrix where you have a lot of wind power that, for example, during a few hours, during 5% of the time in a day, it generates a lot of electricity, which will cost a lot of money for you to find a solution for that 5% of the day, be able to store all the energy. This is a good alternative for this very peak electricities, which costs a lot of money to store. However, so the efficiency of just using electricity to store, it's around 20 to 30% efficient, which is very low efficiency. However, if you have industries around which can supply you with cheap waste heat, or if you have, for example, if you're close to the coast and you have access to deep water at 0 degrees, for example, if you're in Brazil, you can increase the efficiencies to 60 to 70%, which is acceptable. It's similar to pump storage, for example. But this is the main benefit. The main benefit is that the cost of storing a lot of energy in a short amount of time is small. And of course, the cost now is not competitive because there's still a lot of people have to invest, people have to buy, people have to operate these solutions in order to lower the cost. But it's an alternative for the future. It has its niche, but yeah, it's interesting. I think I like that you enjoyed the video, Natalia. Thanks for your feedback. So, as I mentioned before, you have power, energy, and power. So this is cheap in order to quick generation. The storage is also relatively cheap. The most complicated part is to generate electricity from from the cold source. It's kind of similar to I'm not sure exactly the system that they use. I didn't look into detail, but they have to expand, they have to liquefy the air, and it's complicated. So this is more expensive. But for example, if you charge your heating tanks with electricity during a short amount of times, then you can have a longer period to generate electricity because this discharge is more expensive. So you charge very quickly and then discharge slowly in order to make it viable. So any questions about liquid air energy storage? No questions. Let's keep going. Heating thermal energy storage. So I have already talked about some heating thermal energy storage solutions for electricity generation, for with combined heat and power, but also one very interesting demand and one very interesting solution for heating thermal energy storage is basically to have this peak storage. I already talked about them in the first lecture, but they are one of the most implemented solution for thermal energy storage, mainly very cold countries on the north, for example, in Denmark, in Sweden, in Norway. What happens that the temperatures outside are very low during the winter. It's very cold, and in the summer it's hot. For example, in Denmark, it reaches 30 degrees, and people have demand for cooling in the summer. So what happens is that they store with water. They have a huge pit which they fill up with water, and the sensible heat of water cools down to 0 or heats up to 25 degrees in the summer. So in the summer, you have air passing through and heating this water, which heats up to 25 degrees. And in the winter, when it gets very cold, they have a lot of hot water, which is used for district heating. So they have this town here, which demands a lot of heating in the winter. So then they have this stored heat from the summer. So it's a seasonal solution. So the coefficients of performance, the COP, very high, because you just need to, in the summer, you have to pass ambient air in order to heat this heat storage, and then in the winter, you just use this hot source in order to heat up district solution. So this means that capital costs are high for this, so it costs a lot of money for you to build these systems, but to operate the systems is cheap because you're literally just storing energy from the summer and using it in the winter. A similar solution, which I also mentioned, but I didn't go too much in detail, is aquifer thermal energy storage. So there is a lot of research, there is a lot of papers. If today you put aquifer thermal energy storage in Scientific Direct, you get several papers, and it's becoming very popular in Europe, particularly, which you have 2 different locations which are not connected, aquifers, which you can, during the summer, you have one aquifer, which is cold, so it was cold during the winter, last winter. So you get this cold that you stored, and then you use for cooling, for heating up the house. And then the heat from outside is then stored in another aquifer. And then in the winter, when you need heating, the heat that you stored in the summer in an aquifer, so literally water on the ground, so groundwater, an aquifer, you use this hot water in order to heat up the building, and then you cool down the other aquifer. So this is also a solution with very low operation costs and high capital costs. This is particularly interesting in Europe, where you have the interest rate now is 2%, 3%, 1%. So money is literally free if you guarantee that you're able to pay in the future. If your business model shows that you can make money with this in the future by lowering heating bills, it's a great solution. So, for example, these highly capital-intensive solutions are particularly good for countries that have low interest rates. And countries that have high interest rates, they usually tend to go for solutions which are cheap but very expensive to operate. So this is the aquifer, thermal energy storage. Also not going to go through too much in detail because this is not so important in Brazil, for example, because the change in temperature for summer and winter is not so high to make this a viable alternative, particularly with high interest rates. And maybe for example, in Curitiba, maybe in locations which is particularly cold, this could be a solution. Even maybe in Porto Alegre, which has cold winters and hot summers. However, you would need district heating in order to make this viable. This is not a solution that you will build for a house. This is a solution that you build for district heating, similarly to the pit storage. In Brazil, we don't have many district heating alternative solutions, though also one reason why this is not particularly interesting for Brazil. This could be, for example, applied in industry. For example, you have an industry that has a lot of heating demand or cooling demand, or heating and cooling demand, which is even better. In Porto Alegre, where you have seasonal thermal variations, and this could be a solution, for example. Another thermal energy storage solution, which makes solar heating panels viable, is literally this tent here, which usually have phase change materials, so they can be latent heat storage, or they can be chemical materials that vary. I looked in Alibaba for some solutions. They have this nice solution you can buy for $200, and then you won't have to, if you live in a house, of course, you won't have to pay gas bill anymore because you're heating only for cooking, of course. But your demand for washing, your demand for shower will all be met with solar energy. So solar energy in Brazil is massive. I don't know why Brazil doesn't invest in this. This is a no-go situation. Like, you invest in this, in 2 years, 3 years, you have your money back, because it's particularly in Porto Alegre, in the south of Brazil, where they use liquefied petroleum gas, LPG, so petróleo I don't know how to say it. So butano, propano, butane, propane, pentane. So these gases, they are 4 times, 3 times more expensive than natural gas. So heating bills are very expensive in Porto Alegre. So these solutions, great solutions. This is more for heat generation, but I added this to this presentation because without the storage tank, this would not be viable. And given this is a storage lecture, I thought they would be interesting to add. Of course, if you put the storage tank on the top of the roof, it will be horrible. So you can also add inside the roof of your house. And it's very convenient to put the storage tank above the panels, because then you don't need a pump, because the fluids that flow through the panel, the density is higher. The density, when it's hotter, the density is higher, so then it rises, and then when it cools down by storing energy in the storage tank, it goes down again with gravity, and then you have a system that works with gravity. You have, for example, your storage tanks on the ground. You have to install a pump, and you have to pay for the pump in order to constantly fight this change in gravity and heat gradients. Yeah, so I addressed the main thermal heating thermal energy storage solutions, which I thought it would be interesting to share with you. Now we're going to talk about cooling thermal energy storage solutions. So the most obvious, basic one is to just freeze water. But as I mentioned, when you change the phase, physical, when you change from liquids to solid, and you want to use latent heat, it's very complicated to be able to exchange the heat. So the thermal conductivity is very poor. You would need some solutions like this, for example, copper coils, in order to improve the thermal conductivity for this ice storage solution to be a viable alternative. I found this solution in Alibaba. I wanted to check with you guys what was the cost, compare for you to have an idea. So this solution would be interesting for example, storing energy at night, and when you don't have much solar power. And the other benefit is that running a refrigeration cycle at night is much better, because the coefficients of performance of the system is higher because the temperature outside is lower. So for example, at night, the temperature outside is maybe 15 degrees, and you want to store energy at 15 degrees to use when it's 30 degrees. The efficiency of the system increases substantially. It's as if you're storing cold energy at night and using it during the day when it's hot. This is one of the benefits. The other one is to store electricity during the night to generate during the day. This is not a good solution for solar power, for example. The solar power generates most of the energy during the day when it's hot. So, for example, this is a solution when you have wind turbine that generates a lot of wind turbine at night, and when the electricity is cheaper at night. Ice storage solution, a good solution for operating at night. For this reason, I'm not sure if you guys followed, but it's very important, this aspect. The coefficients of performance increases. So, for example, you have this solution can store 460 kilowatts of thermal energy. You would use this system to replace an air conditioning system, which usually operates with coefficients of performance of 3. This is the amount of electricity that you save during the day when you melt the ice, which is 152 kilowatt hour of electricity. Then calculating the costs, we have the same costs, $1 per kilowatt hour of electricity, which is literally the cost of the system divided by the amount of energy that you store, that you have in your storage solution can store. This is $255 US. You have the interest rate of 8%, years of operation 15 years, as the advertisement says. You have discount factor of 5 years. the capacity factor 30%. So this capacity factor of 30% would be, for example, if you have this system in Bahia, so in a place where you have you would use it pretty much every day. So in a supermarket in Bahia. So this is a very high capacity factor. As I said, for example, for storage solutions, maximum capacity factor is 50%. So then you have 295 divided by 8, the number of hours in the year they can operate, the capacity factor multiplied by 100, so there you have megawatt hour. So then this costs $13 per megawatt hour. In reals is 71 reals per megawatt hour. So it can be a viable solution, for example, in a location where you would use it with 30% capacity factor. Any questions about ice storage? So it doesn't work very much with solar energy. Anyway, another solution, which is very, very interesting, and I think you guys should literally write down, because you should, if you have time, if you're willing to invest money, if you have money, or you want to start a company, this is an energy company in Brazil. I would suggest you to invest in this. So this is kind of like, not on batteries, not anything. This is a very, very good solution, but it's kind of like installing air conditioning. It's very labor intensive work, but yeah, it will pay off. You'll have a lot of customers because it's a very good solution, which is literally using a swimming pool to cool down your house and using your house to heat up the swimming pool. So you have an air conditioning system, which instead of heating up the air, which usually when you turn on the air conditioning is like a fridge, a geladeira. You have to heat up the environment, but to cool down inside. So if you have an air conditioning, which instead of heating up the air outside, you heat up your pool, what happens that the pool usually is 3 to 5 degrees colder than the average temperature of the day. And the other good thing is that the pool usually stores the cold temperatures from at night, because at night it's colder, so it's already a thermal energy storage solution in whichever house or whoever owns a pool. It stores energy at night. So when you want to run your air conditioning mainly wants to generate during the day. So the pool is still colder during the day. For example, 12 o'clock is much colder than the ambient temperature, which substantially improves efficiency of your air conditioning system. The other thing is that the pools, for example, if you have a week which is very cold, and then you have another day which is very hot, which happens regularly in Porto Alegre, for example, it would take 2 to 3 days for the pool to increase in temperature. So you literally can use the heat stored in the pool from the cold days to use in the hot days. So overall, this system increases the efficiency of air conditioning systems around 20 to 40%. And literally what you need is just to buy a very small heat exchanger and to connect your pool pipe. So you have your pipe, your pool pump, in order to clean the pool that is constantly running. You have to connect it to a heat exchanger, to your air conditioning heat exchanger, which usually is the split that stays outside your apartment. Instead of using a split, a radiative heat exchanger, you use the pool water. So it's water cooling solution. What else? Oh yeah, so the other benefits that you heat up your pool because you're extracting heat from your house and you're heating up your pool. So there are a lot of people that spends money with solar panels to heat up your pool. Don't do this. Install air conditioning. Make sure that your air condition heats up your pool. It's much cheaper than buying solar panels to heat up your pool. Yeah, so if you guys are interested, so this guy talks about the solution in the US. There are several different videos about this. Different companies are making a lot of money with this in the US. And I personally never heard about anyone doing this in Brazil, and it's a great idea. I personally had this idea while writing a paper about swimming pools, which I'm going to go through the swimming pool paper.
Julian, I was going to ask you that if we can make a research for Anel with this.
Yeah.
I don't know if
with the distribution system. So if you have to talk with distribution, so not generation. So you have 3 Anel type of funding. You have geração, transmissão, e distribuição. The distribution people. So it's a PEE. You know PEE? PEE é projeto de eficiência energética.
Yes, yes.
Pesquisa e desenvolvimento em eficiência energética. Maybe you can do PED Anel, maybe, but it will fit more the PEE. But then you have to convince a company that want to invest in this, because generation companies would not be interested in finding a solution for somebody to lower their air conditioning bills. Maybe they want them to have higher air conditioning bills. And the other thing is that they're not in the business of retrofitting people's pools, right?
Yes, it makes sense.
So, yeah, because when you propose a pay idea, you have the company that wants to invest in it, they have to have literally
benefit from it. Yeah.
Yeah, they have to have a return in their investment. They want to make a business out of it. And I don't think one of these companies would be interested in investing in pool retrofits. But maybe they do. Maybe small companies, for example, I don't know, there are some small companies that have wind generation that they have to invest in PED. Maybe they have one wind power plant and they are not affiliated with a big corporation, and then they will decide to invest in a solution that they will make money out of it, and they can make a lot of money out of this. This is a very, very energy efficient, thermal energy storage solution. So watch the video when you have time. I'm not gonna go through because it's 7 minutes, but the guy, these American guys that sell the good in marketing and explain everything. There's very good video to have an understanding. It's very cheap. This retrofit is very cheap. So you won't make so much money because it's cheap to implement. But the person that's going to implement this is going to save 20 to 40% of their energy bills in air conditioning. So, yeah, given that we talked about swimming pools, might as well go quickly through the paper that's I'm writing with some people from Promac. The idea is to use swimming pools that people are not using. So basically, so you had a family, everyone go to university, they leave the house, and then you don't have kids, you're old, and then you will live for 20 years in your house, and then you're not going to use the pool. Pools are usually very expensive to maintain. So then you can turn it into a thermal energy storage solution. So I submitted this paper to Energy Conversion and Management, and it was They requested a lot of major reviews. I submitted the major reviews, and I think they're going to accept because I managed to fulfill all the requirements. So fingers crossed. It was a lot of work to get this accepted. It wasn't very easy. But the concept is mainly during the winter when the temperature outside is very cold, in the winter in countries where have very high seasonal variations, you use the very cold temperatures in order to produce ice slurry. So you don't need to fill up the whole pool with coils, copper coils. You have to spend a bit more money in your energy storage. So the power part of the energy storage solution, which is from electricity produce ice, and then you pump the ice slurry in your pool, and then you fill up your pool with ice slurry during the winter when the efficiency of the system is very high, so much higher. So you kind of store the coldness of the winter in your pool. And then there are several types, several different ways you can operate. In the summer when electricity is cheap, you can use the chiller. You can produce more ice slurry because electricity is cheap. And then when electricity is expensive, what you do, you turn off your chiller. You use the cold that you stored in your pool only to fulfill the cold demand for your house. And another approach is that if electricity is expensive, but you have a lot of demand, very high demand for cooling, you also have to turn on your chiller. But that's life. Sometimes it doesn't make sense to make so this is kind of a base load cooling solution. It's not for peak. Peak is air conditioning. You turn on air conditioning, it cools down immediately. So a pool, an average pool, which usually have 65 meters cubic of ice slurry storage capacity, can store 3.5 megawatt hour of cooling, which is around 30 to 50% of average house cooling demand. Of course, you wouldn't use this in an apartment with sharing with. I mean, if you live in a building with several people, you won't want to freeze your pool. You want to use your pool, but this is for a house where people don't want to use the pool. So the pool will become a storage tank. And a lot of the reviews. So I sent this paper for three journals. Sorry, a lot of them argued about the heat losses. So they're very concerned about the heat losses. And I found a solution which substantially reduce heat losses, mainly on the surface of the pool, where it has the most heat loss, which is when you return the energy, the heat, the hot water that was used to heat up, cool down your house, so the temperature can come back at something like around 20 to 18 degrees. And then you return the hot water on the surface of the whole swimming pool. And what happens is that this surface having 20 degrees will have that the whole pool system will have a 30 degrees temperature difference between the pool and the outside temperature instead of 50 degrees. So this lowers to the half the amount of heat lost through the surface. And then whichever heat is lost from the tank to this section is irrelevant because this water would come back to the pool anyway. So this water would return to the pool anyway, and ice will melt, and that's the way the system works. But if you have this layer, this works perfectly. You could also have the same thing around the whole pool, so a 20 degrees layer, which substantially would even reduce even more the heat loss to the environment. However, it's much more complicated to have this layer, and you have, so you probably have add the hot temperature out here, and then we'll go all the way up, and then we'll come down. It just makes the system more complicated. So, and you also have the ground also works as an insulator anyway for the pool. So this is the most important part. So the materials that are proposed that are used for estimating the heat loss for the system are this vacuum thermal insulation, which is 10 times, which has insulation capacity 10 times higher than the foam that we use in isopor, for example, or the rock wool, which usually used in Europe for insulation, house insulation. This vacuum thermal insulation panels are made of carbon fiber, and they have a structure, very strong structure, which allows them to create a vacuum inside. They're very fragile. You can't really play them very. If you use them, for example, they are usually used in cooling tanks, cooling bags. They're very efficient heat insulations. For example, if you go have a beer, drink a beer, you put a lot of ice, you put your beer, and then you have this cooling isopor. But there's a more efficient isopor, and it's lighter because it requires much less thickness for thermal insulation. But then I calculated the heat loss, and it turns out that with 120 millimeters, so 20 centimeters of thermal energy, thermal insulation with vacuum thermal insulation, you can result in 10% energy heat loss in the whole year. So you fill up a pool full of this ice, and then with this amount of insulation, also this layer here, which reduces the heat loss potential, because the temperature here is 20 degrees when the system, of course, is working, when you're actually cooling the house. However, this solution is mostly interesting for locations where they have very hot summer and very cold winters. Or locations, for example, in Ceará, in Bahia, where the temperature is the same, you don't need such a large storage tank, and it doesn't make sense. This is the proposed solution for the operation of the system. I'm not going to go through in detail, but this is the heat being stored, so ice slurry being produced in the pool. So in the winter, you have most production. In the summer, you consume the ice on the pool. I also developed a method to estimate the potential for this technology. So the main variable for this is the seasonal variation, but also daily daily temperature variations also take into account in this technology. And apparently Iran is the country with the most potential. US has some potential. Argentina, Australia, China, Middle East, some potential in Europe also. Any questions about cooling, energy storage technologies, swimming pools?
Yes, there's a climate that's better. Like you showed that Iran is best, probably because they have a desert climate. Is something related?
No, maybe. I guess they have a desert because they have this climate. It's kind of like the opposite way around. They have such very cold winters and very hot summers. And if you want to run air conditioning there, the temperature is 50 degrees. What happens is that the coefficients of performance will be low, like 2, 1.5. You need a lot of electricity in order to generate the cooling that you need. If you, for example, generate ice during the winter at 15 degrees, the coefficients of performance will be 3, 4, much higher. And then it's just you're gonna need less electricity for your refrigeration system. The other thing is also a storage solution, because you're not going to operate this storage solution when electricity is expensive. You're going to operate when you have a lot of wind power, for example, at night, or even solar power during the day in the winter when the temperatures are not very low.
Yes, okay. Yeah, because I was looking, and it looked like for hot, humid climates as Brazil, it doesn't have like a great potential. Because of that, I asked about the climate.
Also, any other questions about cooling? How many time now? 10 minutes? Okay, so phase change materials. Thanks for your questions, Natalia. They're very interesting, and they make me very motivated to go in more detail about the subject. I'm not sure if you all can follow, but if you can't, just please ask. I don't understand this. Can you explain more this? Or even correct me, because sometimes I'm wrong. I mean, I'm saying things which make no sense. So, very appreciate if you do that. Phase change materials. We talked about molten salt, ice, but also there is this paraffins and salt hydrates, which are also interesting and have different applications. I'm going to talk about the ones that most interesting for Brazil, for example. And kind of like the potential for this technology is in a house. For example, you are in a house, and then the house heats up a lot during the day and then cools down a lot during the night. Is not good. You want to live in a house that maintains an average temperature throughout the day and the night, in order to have a better quality of life, or even if you have air conditioning system, to make your air conditioning system more efficient. So, for example, if you the concrete walls, if you compare with this phase change material, has much lower capacity of storing heat. Wood, plaster, iron, water. So this is the benefit. It has a lot of potential for storing heat from the night to the day, without having to run any. It's not any electricity storage. It's heat storage. Is materials that you put into the building. For example, I found some examples for tijolos that you can add in the middle this phase change material, which will help you to keep your temperature, your house at a certain temperature. However, you have to be very careful which climate you live. For example, if you live in Porto Alegre and you're in the winter and you have the phase change, but then the phase change is at 16 degrees, so it's very cold. And then for you to heat up your house, you have to phase change with heating, So this is very particular to the climate of the region. If you want to add this type of solution for regions that have very high seasonal variation, it's not very convenient, because it might be convenient in the winter, but then it's not going to be convenient in the summer, or the other way around. They have to be very careful, case by case, to see if it's a good solution. And another option to use this phase material is to improve the efficiency of your air conditioning, which, for example, on top of your house, where you have easy access to the air outside, you have air conditioning system which cools down the top of this section of your house, which you have the cooling system here. So you would need two air conditioning systems, but the good thing is that this phase change material is used for storing energy from the night to the day. And then this will increase the efficiency of your air conditioning system overall. For example, in the nights where the temperature goes below the temperature of the phase change material, what you can do, you can just cool down, for example, your material with the air outside. And then the next day, you'll have this phase material, which will increase the efficiency of your heating or your air conditioning, because the temperature that it is input into the system in the refrigeration cycle is smaller, increases the efficiency. So this is another application that can be done with phase change. For example, in Porto Alegre, I suggest looking at this temperature profile, which happened in 2019, so the beginning of 2019, the end of 2019. It would be interesting to have something between 16 to 17 degrees phase change material. And then, for example, in the summer, the phase change is not going to happen because it doesn't get lower than 16 degrees. But if you add your air conditioning system, which will lower the temperature to 13, 14 degrees, then you can store energy at night. Even if you don't want to turn on your air conditioning that night, you can turn on the air conditioning system to increase the efficiency of your cooling system, because you will change the phase of your material that you use for thermal energy storage. However, in this particular moment, in the end of the summer, you can use the phase material change without even turning on the air conditioning system. So during cold days, cold weeks, you just cool down and store the cold in order for during the day. And for example, the most interesting phase is the one that crosses the most of these peaks. Low peak, high peak, low peak, high peak. You've got as many of these that you cross, you don't need any electricity for air conditioning. You just store energy by phase change. But this doesn't happen so much in locations where you have this seasonal variation. So phase change is not great for. It's great for example, in people that live in the equator, where these values go up and down, and you can. But even in countries with seasonal variations, you can use this in a system with two air conditioning like this, and it can still work and increase the efficiency. For example, here the efficiency is not so great. Here the efficiency is much better in this case. And I wanted to calculate if it makes sense, if you want to invest on this, for example, and then the cost for storage is very high because phase change material is expensive. So the phase material for example, energy storage of a house, daily energy storage demand. So this is much more expensive than, for example, a lithium-ion battery. However, it operates for 20 years, which is good. But then it turns out that the cost, also assuming 20% capacity, maybe it would be even lower because it's not used at full potential the whole year. So the full potential is only used during these times. So there may be even 10% capacity factor. But with 10%, even with 20% capacity factor, shows that this solution is very expensive. It's not a good energy storage. We have 15 minutes. I'm going to go through seawater air conditioning because I wrote 2 papers about it. There is thermal energy storage solution within this technology. So the idea is that seawater at 700 to 1,000 meters deep is cold around the world because in the poles, North Pole, South Pole, the temperature is very low, and then this reduces the temperature of the bottom of the ocean around the whole world. This actual view, there is a view of this section of the ocean. In front of Brazil, is around the middle is here. So it's around 700 to 1,000 meters that you reach this 4-degree temperature. This type of I didn't talk about the technology. Sorry. So the idea is to pump water from the deep sea, which is at 3 degrees, to the coast, and then exchange the heat from the seawater to fresh water or different coolants in order to use for district heating or district cooling or cooling of industrial processes, several other cooling cooling solutions. And then, of course, the hot seawater has to be released, and you don't need to go all the way down to the bottom, but also you should not release here because you have environmental impact. So you should release this brine at altitude of 50 to 100 meters deep. Another benefit of this brine is that it comes with a lot of nutrients from the bottom of the ocean, which can enhance fishery and fishing activity. So there's also this benefit. But of course, environmentalists will not be happy with this because even though you might have 1 or 2 fishes there, they will be impacted because the ecosystem will change. Even though with the alternative you have much more fish, environmentalists, they don't like to change the environment. Anyway, let's go. I have a couple more slides. I have 10 minutes. So the main potential is around this area because it's very capital intensive. So you have to put a lot of investment. The capital costs are very high. Operational costs are very low. So it's locations close to the equator where you have a lot of cooling demand, and locations where you have the continental crust is small. So this is why Brazil doesn't have so much potential, because in locations the continental crust is 40 kilometers. In the south of Brazil, the continental crust is 100. Here you have 10 kilometers. In Fernando de Noronha is red because you have 1 kilometer to reach the deep sea water, which makes it cheaper because you need less pipeline and less pumping costs. So this is a potential for the coast of Brazil. These yellow lines show locations with shorter than 20 kilometers. So you have these locations shorter than 20 kilometers, and that's all the potential for Brazil, because Brazil has a very large continental crust. So 1 meter cubic per second of seawater at 5 degrees, which can provide 41 megawatts of cooling demand. And this is equivalent to something like around 21 megawatts of turbines, wind turbines, assuming that the air conditioning that they use is 2, so they have a coefficient of performance of 2. So I'm talking about thermal energy storage. I'm not talking about refrigeration. I'm not sure if you guys know what coefficient of performance is, but I'm going to quickly explain to you. It's literally, if you have 1 megawatt of electricity and your air conditioning has 2 coefficients of performance, what happens is that with 1 megawatt of electricity, you get 2 megawatts of cooling. So this pipeline, 1 meter cubic per second, is equivalent to 21 turbines, 21 megawatts turbines, 68 football pitches of solar power. It's a renewable energy technology. no one talks about. It generates renewable cooling energy. Is equivalent to a hydropower plant with around 20 meters head and a flow rate of 100 megawatts per second, which is equivalent to one of the dams in Paranaíba River. There's a huge potential for energy for cooling. And the storage solution for this technology is much better to have a tank which is filled up with seawater and lowered with seawater, because you're constantly pumping seawater from the bottom of the ocean. So you have a lot of seawater available. It's not a good idea to use sensible heating in this case. So in this case is the mass balance. Just add seawater, and then when you need, you add seawater when you have cheap energy, and then when you don't have energy is expensive, you stop pumping, and then the level goes down. I skipped one. Right, sorry. Yeah, so this is an important slide actually, which shows the coefficients of performance of the system. The coefficients of performance is 41, which means that you put 1 megawatt per hour in order to pump water from the deep sea, and you get 41 megawatts of cooling. So very efficient. And this is the benefit of this technology. However, the problem is it's very capital intensive. So you have to put a lot of money up front, but the operation cost is very low. So particularly now the investment costs are low in Brazil, this could be a solution to be implemented in Brazil. So I have recently published a paper which talks about this possibility of increasing the pumping capacity. And by increasing the pumping capacity, you can increase the velocity. By increasing the velocity of flow in the pipeline increases the energy consumption. Of course, the energy consumption is not as high as air conditioning. You cannot compare with air conditioning, but it's a little bit higher. But at least you don't need to invest in a new pipeline, which would be much more expensive because the capital costs are very high for this pipeline. So the proposal is that you have if you invest in more pumping capacity, you can pump more when electricity is cheaper, and then use electricity from the grid is a demand side management solution, where when you have electricity, you pump more. When you don't have electricity, you pump less, and you use these tanks to store the seawater in between these the demand in order to meet the demands for cooling with this system. Going quickly because we have 5 minutes. Right. So the main uses is airports, hotels, data centers, shopping malls, industrial processes. So very high energy intensive for cooling. So locations close to the equator where you have a lot of cooling demand, concentrated cooling demand, which is kind of these type of uses. And in Brazil, I was going to go through, but we don't have so much time. In Brazil, there is a lot of potential for grain storage because grain has been the commodity that has risen most in cost. And for example, the most use of soybeans. Soybeans is the one that increases the most. Soybeans mostly used to feed animals for protein, so that we can eat protein. US and Brazil produces most of the China supply. Brazil is expected to substantially increase production compared to the US in the next years. US has a lot of storage, seasonal production. So they have a lot of storage, which is a lot of great benefit for them. Brazil doesn't have storage enough. So the US, they had, for example, the tariffs imposed, lower the the amount of money that they could make with soy, so then they could store. So they didn't sell, they stored all the soy that they have. They have capacity for 4 years of storage, compared with their plantation, because they have a investment cost is very low. You can invest, money is free, it's cheap. You just invest in infrastructure. So this is a great benefit for them because, for example, in this case, the U.S., Trump sends a tweet which they're going to embargo, they're going to create taxes, and then the prices plummet. And then in Brazil, it wouldn't even pay the costs of, for example, transporting soybeans to the ports, because given that we don't have storage, you have to waste all these products. So storage is a huge problem for Brazil. Brazil needs a lot of grain storage. And the storage capacity, it was usually equivalent to the production, a little bit higher, but nowadays it's even lower than the production of 1 year is usually. So FAO suggests, FAO is the United Nations agency that deals with agriculture, suggests 1.2 times higher, which is something like this or this, but now it's lower, the amount of storage that we have. And the other thing is that the storage in Brazil is not very good quality, because we dry the product, but it's still at 40 degrees. So it cannot sustain so much time being stored, because the quality of the grains will reduce because the temperature is very high. Even though you can still, it doesn't, a semente não nasce, né? Você não tem total dela. The quality of the soybeans are affected. So I'm talking about grain storage here because of this. We have a lot of cheap energy that can be used from the bottom of the ocean to cool down storage tanks from soybeans. So we're talking about soybean storage. We're also talking about thermal energy storage, because we also have to keep the soybeans cold. And so soy industry is literally a huge chunk of the Brazilian economy. So there'll be a lot of people interested in solutions for soybean storage. So you can think of a thermal energy storage solution for soybeans storage. You can also consider using these seawater air conditioning solutions for soybean storage. I'm just putting out there a huge demand that Brazil will have for thermal energy storage. Is to improve, to reduce the costs of storing soybeans. Another last comment is the seawater air conditioning also can be used to improve the efficiency of production of hydrogen, liquefied hydrogen. So hydrogen, you have to lower the temperature from atmospheric temperature to minus 253 degrees, very cold. If you lower to 3 degrees instead of 30 degrees on the surface, you'll have something like 10 to 15% gains in efficiency for liquefying hydrogen. Right? These are the two alternatives that I think that seawater air conditioning should be looked into detail for Brazil. That's huge potential. The conclusions of the lecture, we looked at combined heat and power, and this is currently the best viable solution for thermal energy storage, to use thermal energy storage in combination with combined heat and power at different ways, whichever meets the demand for heating and cooling. You have the possibility of using solid oxide fuel cells with combined heat and power, particularly in small customers in the future. So instead of you having a boiler in your house, you have a solid oxide fuel cell with a thermal energy storage solution that will generate electricity for you and provide with your heat demands. We looked at several solutions for storing electricity seasonally. So store the coldness of the winter for the summer when it's hot, and store the hotness of summer for the winter when it's cold. So long-term seasonal thermal energy storage is very important, particularly in Europe and maybe even in Brazil. Talk about pools being used to increase the efficiency of air conditioning systems, which I personally think that this is a great idea if you have a pool and you want to lower down your energy bills. We looked at phase materials, phase change materials. They have good potential, but still not viable. Costs still need to lower. And also, you have to find a good solution for your energy storage demands. And in the end, we talk about seawater air conditioning, providing cooling or grain storage in Brazil. Sorry that I had to rush in the end. I wasn't really thinking that I would exceed the time. But thanks so much, guys. It was a pleasure to give you these 8 lectures on energy storage. I hope that you enjoyed. I tried to be more to give you as much information and content and knowledge as possible on the topic. It would be great to hear your feedback. If you wanna let me know now or by email, like what you like, what you didn't like, for me to prepare the next lectures better. Whichever topics also you're interested. If you're interested to work with this in your thesis or in anything, in my opinion, or a project, or even the projects that you need to make next year in January. Please keep in touch. Yeah, any questions,
Júlio.
guys? So, yeah.
Júlio,
Hello.
tá escutando? Tá. Alô?
Tô escutando.
Escuta bem?
Olá, Flávio, tudo bem?
Tá escutando?
Tô.
Tudo bom? É que eu cheguei atrasado na aula aí. Hoje é a última aula, né? Isso, né?
Isso, última aula.
Tá.
Mas,
Umas considerações. Não, sobre até um feedback aí da aula, eu acho bem interessante o conteúdo, o material, muito bom. Só como sugestão, fosse possível receber